Optionally, using one of the CCP modules here, we have seen that we have two CCP modules as on other microcontrollers. So one of the CCP modules can be used for power factor correction for power sensitive applications. So this block shows here a power factor correction, which can use one of the CCP module or cassette compare and PWM module and control the power factor. Moving on to next slide, we will see what is the sensorless control of a brushless DC motor and what are the advantages and how we can implement using PIC18Fxx31. Sensorless control of brushless DC motor gives many advantages. Most importantly, lower system cost. Every phase develops a voltage called back EMF that opposes the power applied to the phase. During the non-energized phase of the sequence that we have seen earlier, this back EMF crosses from positive voltage to negative voltage or vice versa. From this zero crossover point, rotor position can be determined and used for commutation. This method eliminates the requirement for sensors for commutation that we have seen earlier. Hall sensors can be eliminated with sensorless control of brushless DC motors. This increases the reliability of control, but it requires some additional hardware on the drive side and additional firmware overhead on the microcontroller side. If you see this block diagram, most of the hardware blocks remain same. The PWM remains same. The current sensing and overcurrent fault detection remains same. Motor current measurement, which is connected to ADC channels, remains same. And temperature sensor optionally, which can connect to one of the ADC channels, remains same. Only the difference is adding a block to detect back EMF zero crossing. The back EMF zero cross detection can be done in different ways. Following slide shows a couple of methods that can be implemented to achieve back EMF zero cross detection. Let us see what are those methods. Today we will discuss three different methods to determine back EMF zero cross point. First one is comparing the back EMF signals with respect to half of the DC bus, as shown here. Every sequence has two windings connected across the power supply and third winding left open. This we have seen in earlier sections. The back EMF generated in the non-energized winding is compared with respect to the half of the DC bus. This gives a fairly good result when the motor terminal voltage is approximately equal to the DC bus voltage. So using a comparator, the back EMF signal is compared with half of the DC bus, and the back EMF signal here seen is converted as a square wave, and based on the transition of each of these back EMF signals, we can determine the switching sequence. If the DC bus voltage is disproportionately high, in this case, the crossover point may drift away. So this is a disadvantage with this method, making it difficult to determine a workable commutation sequence at all speeds. So what is the solution? We will see the second method, which gives a fairly good result compared to the first method. So in this method, we will compare the back EMF signal with respect to a virtual neutral. We will generate a virtual neutral using 3 resistor network as seen here. So this point will act like a virtual neutral for this circuit, and this is compared with back EMF signal using a comparator, and this gives a square wave and combination of 3 different 3 inputs here. We can determine the commutation sequence. This has advantage. This makes it comparatively easy to determine the zero cross point at all measurable speeds. And third method is using high-speed ADC that we have on PIC18Fxx31 devices. The back EMF signals are attenuated and read directly using on-chip high-speed ADCs that are available on PIC18Fxx31 devices. This gives a great flexibility in determining the zero crossover point. The firmware should read the back EMF signals continuously and compare with the digital value corresponding to the zero cross point. Also, digital filters can be added to filter out the spurious signals that may come due to high frequency switching. So this gives great flexibility in determining the back EMF zero crossover point, because the control lies with the firmware. However, there is a disadvantage with the back EMF sensing itself. That is, at low speeds, the back EMF developed is very low in amplitude, which makes it difficult to determine a zero crossover point. In this condition, motor is started in open loop, and when sufficient back EMF is built, the control is shifted to closed loop control. This concludes the presentation, and today we have, just to summarize today's presentation, today we have seen an overview of motor control solutions from microchip, and we have seen PIC18Fxx31 peripherals that are useful for motor control application, and we have seen an overview of PIC18Fxx31 devices. Also, we have seen brushless DC motor control using PIC18Fxx31 in open loop, closed loop with Hall sensors, and with quadrature encoder. Also, we have seen different methods of sensorless control and different schemes to determine back EMF zero crossover point. Next, I will list few resources that are available from microchip. We have few app notes on brushless DC motor and motor control. First one is AN885, which gives few fundamental details of brushless DC motor, and AN899, which explains in detail about brushless DC motor control using PIC18Fxx31 devices, and the third app note is AN857, which is titled Brushless Motor Control Made Easy using other microcontrollers from microchip. Also, we have a demonstration board and development board called PIC18MC, which is a completely isolated board, and this can be used with the debug tools like MPLAB ICD2 and MPLAB ICE when the board is connected to the power or when the board is live. And also, this is a low-cost design, and this is ideal for the designers to start with. All this information is available on our microchip website, so please visit us at www.microchip.com/motor, and thank you for listening.